15,000 feet underground, a drill bit crushes solid rock. At this depth, it operates against 10,000 pounds per square inch of formation pressure, while suspended beneath 300,000 pounds of rotating steel. Managing those extremes requires a highly calibrated machine. A modern drilling rig operates as a single dynamic system. The surface equipment and the deep earth environment are locked in a continuous feedback loop. The principal driller monitors surface gauges for hook load and standpipe pressure, tracing the subtle mechanical echoes that climb back up the string from thousands of feet below. To understand how this equilibrium is achieved, we will construct a rig from first principles. We have to solve 5 escalating physical problems, starting with the sheer mass of the drill string. The first constraint is gravity. We must suspend hundreds of tons of steel pipe over an open hole, using a wire rope that possesses a breaking strength of only 40 tons. The primary purpose of the hoisting equipment is to manipulate that massive weight, maintaining a perfect, artificial equilibrium between surface mechanical power and subterranean physics. The load path flows through a precise sequence of structural links. The drill string hangs from the swivel. The swivel is supported by the bales. The bales hang from the hook, which transfers the entire load into the traveling block. If any single link in this chain fails, hundreds of tons of steel plummet to the bottom of the hole. A 12-line reeved system between the traveling and crown blocks divides a 250-ton load by 12. A 40-ton rope can now carry it. The trade-off is speed. Lifting the block 1 foot requires spooling 12 feet of line. Mechanical advantage multiplies force, dividing speed. Holding the weight is only half the mechanical requirement. The string must also rotate to drive the bit, while simultaneously sliding vertically downward as the hole deepens. For decades, this was accomplished using a Kelly, a heavy, flat-sided bar that passed through a matching rotary bushing. The flats transferred rotational torque while allowing the pipe to slip downward freely. Today, automated top drives accomplish this directly from above, suspending and turning the pipe simultaneously. Every time a new section of pipe is added, the connections are driven together with up to 30,000 foot-pounds of makeup torque. To protect the expensive drill collars from the galling and tearing caused by constant thread wear, engineers insert a bit sub, a short, deliberate sacrificial connector designed to absorb the damage and be thrown away. Making these connections historically required a crew to throw heavy chains around spinning pipe, exposing workers directly to extreme rotational forces. Pneumatic Kelly spinners and hydraulic power tongs replaced this manual labor with remote, machine-applied torque. The hoisting and rotating architecture acts as the rig's musculature. It scales human input to meet the physical demands of geological weight and density. Below the surface, the physical metal of the drill string is insufficient to hold back the earth. The primary structural barrier against the formation is fluid, a highly engineered, dense liquid known as drilling mud. The mud pumps drive fluid down the drill string, out the bit nozzles, and up the annulus. Drillers calculate this exact volume in barrels per foot. Returning fluid must perfectly match the volume pumped down, or dangerous pressurized gas could be entering the well. As the mud travels upward, it must carry crushed rock cuttings with it. Gravity constantly pulls these cuttings downward, a measurement called slip velocity. The upward flow of the fluid must be fast and viscous enough to overcome that slip velocity and sweep the debris to the surface. If the annular velocity drops, the cuttings settle. They bridge across the narrow gap between the pipe and the wall, completely blocking fluid flow. This creates a pack-off. Circulation stops, pressures spike, and the drill string is physically cemented in place by its own debris. To prevent the mud from becoming too dense with rock, surface equipment strips the solids out. The returning fluid pours over vibrating shale shakers to remove large cuttings, while centrifugal hydrocyclones spin the fluid to extract microscopic silt. The fluid system is the rig's blood supply, managing the paradox of keeping a hole open while rock is continuously removed. When the hydrostatic weight of the mud column fails to hold back the reservoir, highly pressurized formation fluids flood into the wellbore. This influx is a kick. Left unchecked, it accelerates to the surface and destroys the rig. At the first sign of a pressure imbalance, the driller activates the secondary control architecture, the blowout preventer, or BOP stack. This animated diagram builds the stack from the wellhead up. It relies on layered redundancy. The top layer is the annular preventer, utilizing a reinforced rubber element that can instantly close around any shape or size in the wellbore. Below the annular are the ram preventers. Pipe rams close with steel blocks shaped to seal against specific pipe diameters. If all other barriers fail, the shear rams activate. Two hardened steel blades slice cleanly through the drill string itself, sacrificing the pipe to permanently seal the bore. Sealing the BOP stops the influx, but it leaves a massive pocket of highly pressurized gas trapped underground. To kill the well safely, the crew pumps heavier mud down the drill string, forcing the gas out through a specialized bank of heavy-duty valves called the choke manifold. The choke operator restricts or opens the flowcoth to bleed off the influx. By maintaining a perfectly steady drill pipe pressure on the gauges, the bottom hole pressure stays locked at its target, preventing further gas from entering while the initial kick is safely removed. Once a section of hole is drilled, it cannot remain open rock. It must be lined with steel casing to prevent the walls from collapsing and to physically isolate freshwater aquifers from high-pressure oil and gas zones. This diagram maps the telescopic casing program. The largest diameter conductor pipe protects the surface soil. Inside that, surface casing shields the water table. Intermediate casing isolates unstable geological pressure zones. And finally, the production casing carries the payload to the surface. Lowering steel into the hole provides the frame. The annulus between the pipe and rock must still be filled with a precise slurry of cement. To prevent the cement from mixing with the drilling mud already inside the pipe, a cementing head sits at the surface. It drops solid rubber wiper plugs ahead of and behind the cement slurry, keeping the three fluids perfectly isolated as they are pumped thousands of feet down the casing. At the very bottom of the casing string sits a float shoe. It contains a heavy ball and seat check valve. The high-pressure pumps force the cement down through the valve and up into the annulus. Once pumping stops, the heavy hydrostatic weight of the cement tries to flow backward, which slams the ball against its seat, locking the cement in place. The hardened cement and nested steel turn a temporary excavation into a permanent high-pressure industrial conduit. When the Drawworks lowers a 300,000-pound load through a 90-foot stand of pipe, it releases 27 million foot-pounds of energy. The laws of physics dictate that this kinetic energy must be converted into heat. If the driller relies entirely on primary mechanical friction brakes for descent, the steel bands absorb industrial furnace levels of heat. This triggers brake fade. As the friction blocks overheat, their grip drops to near zero. The brake handle feels exactly the same, but the load continues to fall. To manage this thermal limit, rigs employ auxiliary brakes. Using either water resistance or electric eddy currents, these systems absorb the massive energy of the routine descent continuously, leaving the primary friction brakes cool and ready for the final stop. Thermal and fluid physics expose other limits in the system. If a driller observes a gradual, unexplained drop in standpipe pressure, mud is actively eroding a hole through hardened steel somewhere miles below the surface. The most catastrophic mechanical failure on the rig floor is the crown-out, hoisted in the traveling block directly into the stationary crown block, snapping the line and dropping the entire assembly. Every rig is equipped with an automated toggle switch to cut the Drawworks power before impact. Almost every crown-out occurs because an operator bypassed that automated safety device to trip pipe faster. The mechanical architecture is highly resilient, but its physical and thermal limits are absolute. The system requires strict operator discipline to survive. A drilling rig is a single engine purpose-built to manipulate gravity, pressure, and torque. The Drawworks, fluid circulation loop, and BOP stack operate dependently, balancing the power generated on the surface against the severe reactions of the earth. To the principal driller, the gauges on the console provide a continuous stream of data. A sudden fluctuation in pump pressure or a slight loss of hook load indicates the thermodynamic equilibrium has shifted miles below the surface. Subterranean drilling is the art of mastering equilibrium at the very edge of mechanical and fluid limits.